And with that, further ado, let's kick off our exploration of innovation by our first speaker. I would like to welcome Gerd Teepe from CELTRO. Gerd, please take the stage.
Thank you. So let me go and share the screen, but you have to unshare. Okay, can you see this in full screen? I hope so. All right, my name is Gerd Teepe. I am a semiconductor engineer by formation. I have been working with semiconductor companies all my life long, Motorola, AMD, Global Foundries. And then I decided to start my company with a few friends, and some of them you see on here. So this is our team. We are a bunch of doctors and engineers and medical device persons and finance and mergers and acquisitions people. So it's we have been working in the past. Most of them we have a long-standing background, and so what we have started is, so this is the team. CELTRO is a startup company. We're born on an idea which I'm going to develop in a second. Fundamentally, we want to remove the batteries from implants and open a whole new era in medical technologies. So that's what we are striving for, and and we have found in nanodimensions a perfect partner to go prototype and also hopefully move this into production once we are qualified. So what are we trying to solve? The problem is the problem number one is batteries. So batteries number one fail, but also they're big, and number three, they have to be replaced. So at some point in time, you have to undergo surgery and replace the piece, and that's gives it a limited lifetime. Number two problem is leads. So leads break, leads corrode, they clog up. Leads are medical problems, so we are trying to eliminate leads also, and we are trying to solidify basically the interface into the tissue. That's what we are trying to accomplish, and this is so there's a clear need statement for what do we want to do. Looking at pacemakers, which is our first product we are trying to build. The yesterday piece is not entirely correct because it's still in use today. So pacemakers are being implanted under the shoulder, and then through the leads go through the veins into the heart and are being fixed there. And there is not only one lead. Typically, there are two leads in the heart, and sometimes even three leads. And but what came up in the meantime is catheter implantable devices. So they go through the groin, basically a tube through the blood vessels, and they are being pushed into the heart and then anchored there. They even have some big medtech companies even have developed them to a sophistication that these you can put in several of those devices and they communicate to each other. So that's one thing. What we really want to achieve is we also want to be catheter implantable, but as at least more than half of the volume is being taken up by battery. If we are able to remove the battery, the miniaturization will move forward, and we would be able to make a lot smaller devices than what is able today. So this is really the point which we are trying to address. So how can this be achieved? So we have found some method to collect energy from tiny sources, and then we put some patents up, and they returned to us a piece of paper saying, oh, there is already harvesting methods. No, one is from the environmental, and this is on the left side here. Some people implant solar cells under the skin and derive energy from there, or there's an infrared radiator, or there's wireless energy transfer. This is all being used at this point. There's also experimentation on human energy harvesting, like kinetic energy, a magnet moving in a coil, for instance, or thermal energy. If you have a source and a sink of temperatures, you can derive energy. But what we really do is taking the electrics from the cells and take it from there. And this is why our patents passed pretty easily, because there was everybody was focusing on something else, and electric was deemed to be too small to be usable at that time. And we think it's usable. And what we really look at is that every cell is an electric battery, and there is a kalium-natrium exchange on the cell, on the cell metabolism. And what if you look at the inside versus outside cell voltage characteristics, then you find that there is a swing of almost 100 millivolt between inside the cell over the cardiac cycle. The thing is, we cannot access the inside of the cell. The cell is not stupid. It will either die or reject. And so what we can do is we can go into the intercell space and receive from what the cell pushes out as ions into that intracell space. And that creates electrochemical potentials which we can pick up. So that's the that's the essence of the game, and we don't receive these the full swing of what is happening in the cell, but we receive a portion of it, and we think it's good enough to live with that type of energy. So and then if you consider that already the left ventricle has about 5 billion cells, then you can imagine, and an avalanche effect, and then you can imagine that one cell kicks off other cells, kicks off more cells, and so forth. So it's really coming down as an avalanche, which then has to be fed back into relatively small amounts of energy, kicks off the whole heart action. So, which means that if we pick up energy at certain intercell spaces here, which are the red markers, and we collect this up, we just have to collect more than what we need to initiate the cycle. So that's basically the concept. And with this, we've looked at semiconductor technology, and we found out that basically the technology to do this is already there. This is pretty much an all-over-all chart here of the semiconductor universe. If you look at the power levels on the x-axis from picowatts to watts to 10 watts or 100 watts, and the clock speed on the left side, you find that dynamically there is a dynamic and static power consumption. So let's focus on the dynamic power consumption. The dynamic power consumption is widely proportional, and what we find today is that with 1 watt you can operate 1 teraops of operations. 1 teraops is 1 billion operations per second. So it's pretty awesomely large what you can move in terms of data. but 1 watt is a lot too much, is by far too much. The IoT space is maybe running in a milliwatt space, and applications like wristwatches, they are running in the microwatt space, and where we want to land is the nanowatt space. So fundamentally, this chart shows that the technology is already there. The only thing is, what is not opened is the application space. So dynamically, the power is there, the capability of entering the nanowatt space is there, but it hasn't been done because, well, basically there has not been many applications using this. But from a dynamic leakage standpoint, things are fine. And then there is another aspect, and this is the static leakage point. And the static leakage point is very much linked to device physics. And up to 20 nanometers, the structures have been looking like this. There has been a gate. The yellow piece is isolator, and the source and the drain and the substrate. Now, between source and substrate, there has been, normally there is a diode buffering off the separating the source from the substrate, and diodes, as you know, are leaky. So there can be very low leakage, but there is some leakage current. And now new technologies have come into play, which actually alleviate that problem. And here on the left side, you find a structure, a modern structure with something is called box here underneath the source and the drain. The box is the body oxide. And in fact, there is an oxide underneath the source to the substrate, which means that the isolation potential is a lot better than what we used to have. So there's only then something which is called channel leakage between source and drain. So there's the electrostatics, which control the transistor. But we're getting that type of current is getting back into a design parameter rather than a physics parameter. And so the other thing, so this is called FD-SOI, fully depleted SOI technology. If you take this structure, source drain, which is horizontal, and flip it by 90 degrees into the vertical, then you get a structure which is called FinFET, and then you push the gate not from the top, but from the sides, and you get pretty much the same thing. So there are FD-SOI technologies available in 28, 22, 18 nanometer. There is FinFET technology, which is going beyond and much smaller. And we believe that the old bulk technologies don't lend itself to what we want to do, but we need to either go to FD-SOI or FinFET technologies. But the good news is Moore's law is helping us. So as the miniaturization moves forward, we have, and this is something which technology wasn't able to do a few years ago, is now able to do that, that we actually can reduce the power into a domain where we can operate dynamically and also statically. So with this, let's look at the devices. What we really want is that we use the concept of the catheter implant, but go and create a device which is implanted for life. Which has full pacing capability. And what you find is, from a medical standpoint, that this heart support mechanisms work in the fashion that there's one heartbeat is missing, then 2 heartbeats are missing, then maybe a longer stretch of heartbeats is missing, then people faint. And this is a clear indication that they need a pacemaker. So so what could then be done is, in the future, is that an implant like this is a life enhancing device which prevents this type of behavior. Also, It will drive down the size, it will drive down the cost, it will drive down the base of implants, and also if we come down in cost, it will widen the geographic penetration by quite a bit. So we foresee that with this type of technology, the market will grow tremendously. So so now we have started to work on prototypes. And this is something which we've done with nanodimensions. And the first thing which we've done is we printed a so-called needle holder. So what you see here is you see a holder, a plastic device, which was 4x4 probe array. And this is where we have been placing needles, which we have been manufacturing at a needle manufacturer. So we have been placing these needles here into this holder, and then we have been printing over this. And it's a bit tough to see, but Nanodimension has a AME technology where they can print a dielectric and they can print a conductor. And printing the dielectric over the head of the needles fixes them in the dielectric. And that was one big question which we had: can you do this? And is it good enough? And we found out we can do it, and it's good enough. And so we printed 4x4 needles, and we found out that we can perfectly connect them. The mechanical stability is there, and so we found that with nano dimensions technology, we have a very fast path forward. Now, what we really want to do is something like this. So this is one of the geometries which we might do. So if we can print 60 needles, we can also print 100 needles. And with this technology, we can move forward relatively fast into something which we need. And so this is gray here. This is completed, these phases. So what we need to engage on now, we are engaging on now with nanodimensions is phase 3, a full prototype on with lots of needles, catheter implantable. And once we are done with this, we move into final package qualification and into production. We believe that AME has a bit higher cost than other technologies, but as our material usage is very small and our devices are very small, that we will also find a cost-effective solution once we move into production. There is still a lot of work ahead of us because this is not something which comes for free. We need to check biocompatibility things. This has started, this work, and so lots of work to be done, but we are moving forward. So I'm looking on time. This is particularly on the right side, you see the needle sticking out of the dielectric, and this is the top view of this. So we are pretty proud that we were able to achieve this together with nanodimensions. We also made a few off-the-shelf things, because what we really needed to do is to measure in the biology. And this is we also built our own measurement setup because we had particular requirements. This is a commercial pulse generator which we hooked up. This is our viewing software on this, and then we put up. This is initial needle holders, which you can see on the right side is being put into a heart. This is actually a pig, which is with a relatively big heart, which is very close to a human operation already. So here you can see how this is being fixed on the pig's heart, and actually there's a vacuum which fixes the needle holder, but there's also other means which we have experienced in the meantime. There's a landing pad here, And so this is the type of experiences we are doing. But as you know, on the long run, we want to be catheter implantable. And then the miniaturization aspect of all of this comes together. To finalize, we are going after the pacemaker because that's an easy product. It's not easy in terms of qualification, but it's easy in terms of interface. But once we get going on the harvesting, there is other applications like incontinence, hypertension, sleep apnea. So all of these things will be opening we will be opening those markets, and we will move into technology proliferation by licensing our technology. So with this is my last slide, and I'd like to give it back to Natalie. Thanks very much for listening.
Thank you very much, Gerd. Yes, I would like to introduce our next speaker. If he could stop sharing so Edmond Blue could set up his presentation from the University of Alberta, we will look very much forward to that.
Okay, here you go.
Excellent. Thank you. Edmond, the floor is yours. Please share your screen.
Yes. Can you see my PowerPoint?
You can see your PowerPoint, but it's not no. Perfect. Yep. Excellent. Thank you.
Thank you. So thank you, everyone. So my name is Edmond now. I'm a professor in electrical and computer engineering at University of Alberta. I'm also the principal investigator on the artificial intelligence supercomputing hub here as well. So where is Alberta, Edmonton? I'm locating in here. Now, this is the beautiful national park in Alberta that is very famous. And if you have chance to visit, come visit, and I can let me know as well. I can show you around as well. So in summer, we have a lot of sunlight, but in winter, we have a lot of snow as well. So we have a very widespread weather. Now, in Edmonton here, we have almost 30 days to a month per year that we can see northern light at nighttime. Very beautiful. So University of Alberta is a top 5 Canadian university and is a public research university located in Edmonton. It was founded in 1908. And right now we have approximately 41,000 students, including the undergraduate and graduate students. This is the campus of the University of Alberta. Now, I'm in the Faculty of Engineering, and this is our building. All the faculty members sit in this building. Under here, because I'm belongs to the Department of Electrical and Computer Engineering, we have a nanofab that we can manufacturing microelectronics devices such as nanochips or MEMS devices. So last few years, I'm lucky that I'm also in charge of the supercomputing hub that we got a significant amount of money from the government that we build our supercomputer cluster that can help us to work on a lot of AI projects. Now, Internet of Things, so is a sensor and actuators embedded in physical object and linked through wire or wireless network to the internet. So there's of course there's a lot of application as I list in here, just only few, and you can think about it can expand quite a bit. Now, the global market for Internet of Medical Things is growing and expect to change from $34 billion in 2023 up to 260 billion in 2031. So the market is still growing very fast. So one of my application on the using the nano dimension is for my research that primarily looking at the effectiveness of the brace treatment for children. They have scoliosis. So this is a medical disease that showing the three-dimensional of the curvature of the spine. Approximately 10% of adolescents have scoliosis, and 2 to 3% of these require treatment. So brace treatment is the most effective non-surgical treatment for scoliosis. Now, in the past, the goal is to stop the curve progression, but currently, there's a lot of signs showing you can actually improve after you complete the treatment, but it all depends on some parameters, with how much good time the patient use it and how often and how well they use. As you can see in here, this is a big plastic brace, and the children need to wear 23 hours per day in order to stop the curve progression. No, from our previous study, we found that the effectiveness of the brace treatment depends on the quality design of the brace, the risk, the in-brace correction. That means when they wear the brace, if they wear properly, they should show there's a correction. And also, it really depends on how much time the patient wear the brace and how well they wear the brace. So in the past few years, my team have been using AI on imaging so that we can help the auditors to design better brace. As I mentioned, scoliosis is a three-dimensional problem. In the past, people only looking at the PA and lateral view of the radiograph and then think about how to design the brace. And as the AI technology growing, currently we are able to perform the automatical reconstruction of the 3D spine in 5 seconds. And we are able to display it on the screen and also measure all the parameters so that the auditors, those brace maker, can design the brace in three-dimensional and have better quality of control of their in-brace correction. So this example here showing the reconstruction of the spine and also display. So after we have the idea of the design of the brace, as you can see in here from the before and in-brace correction, is so a very beautiful correction in here. And recently we also using the additive technology to make a 3D printed brace. So the brace can make it lighter and lower cost, and this is as effective as the traditional brace. It makes the compliance better, because in the past, those braces are very bulky, and it during the summer, especially on the hot weather environment, it's very, very hot. But using the 3D design or 3D print brace, that the patient feel very more comfort and they will more often, and they will improve their curvature at the end. Now, besides the brace design, we also develop new technology on the imaging that using ultrasound to look at the flexibility. This also affect how much we can push onto the body to correct the brace. And in the past, using X-ray, but because the X-ray have a lot of radiation, so some of the center they try to not getting the flexibility information because they will require extra X-ray taken on these patients. So our group also developed an ultrasound method that we can look at how much correction the patient can get on the bending, and then that will able to determine the spine flexibility. Based on that, we can also design our brace better so that to get the maximum correction. As we mentioned, one of the factors is the in-brace correction. Now, in terms of the monitoring, how much time and how well the patient used the brace, we have a long track record designing a monitor system. As you can see here, the technology change our monitor, keep smaller and smaller, and get improvement and getting the on the wireless as well. So this is the version that we developed in 2017 that have already a small force sensor and a temperature sensor with the Bluetooth capability. And we build it and we are able to embed it inside the brace and we can building it well. Now, the monitor device always like the condition always can be make it smaller, more low power, stay like keep it longer. So then we continue to develop another system that we design a new MEMS 3D stress and strain sensor that based on the microelectronic, and we are able to detect the stress, strain, and shear forces in 3-dimensional. This way we can embed it inside the brace, but at the same time we can put at multiple locations. That will help us to better understand how does the brace work, because in theory the correction of the scoliosis is a 3-point bending. So we need to understand those at least three locations in order to see the biomechanic behind the brace treatment. So we build our MEMS sensor, but at the same time, at the beginning, we're using the standard printed circuit board. Because the circuit board have certain thickness, it reduce some sensitivity of our MEMS sensor. So we calibrate our sensor and we compare with the standard string gauges. We have 10 times of the gauge factor compared to the normal string gauges. So we also test the system in a temperature chamber as well. Now, the thickness of the regular printed circuit board reduces the normal stress sensitivity of the 3D sensor. So the nano dimension the Dragonfly machine help us a lot. So as you can see in this design here, we are able to make the center area thinner so that we can increase the sensitivity approximately by 30%. Now, we haven't optimized, like we still try to optimize the thickness. So from the original, our printed circuit board, regular printed circuit board is 0.8 millimeter. We're using the nano dimension is 0.5 millimeter. So we are able to manufacturing using the ovens and using the low temperature thermal paste, and then we put into the oven to bake the chip, and then we can populate into the circuit board. So we put the unit inside the brace. We have the Bluetooth to communicate it. We upload the data to the cloud, and the physician able to getting the information from the cloud and then provide the feedback to the patient saying, oh, you need to wear properly or wear more often. So that hopefully it will improve the treatment outcome as well. We also using 300 patient data that try to predict the effectiveness of the brace treatment based on the AI model. So we using the XG boost using 230 data set. One of the major components, as we can see in here, is the compliance. So how much time the patient wear the brace. Now, we still haven't implemented the force yet because up to today, we really don't know what is the optimum force yet. So we still investigate how to determine the optimum force correlate to the maximum correction. At the same time, is tolerable by the patient. But based on this, we already have a very good model that can have around 80% accuracy on predicting the treatment outcome. Now, of course, there's still a room to improve. So we are still working on it and hopefully improve the treatment effectiveness. Now, in terms of other application, we also using the nano dimension machine. We print a full bridge strain gauge sensor that we try to explore and compare with what we built on the MEMS. The cost in using this may be lower, and also we can manufacture in-house as well. We don't send to other center. Also, we have another project that building a sensor, a stand sensor, and the width is only 1.68 millimeter, and the width is about the same. It's 1.68 millimeter. And this is another application that I'm working with a group of surgeons as well. So that one I need to keep a little bit secret because it's still in the early stage. So this is our application on the nano dimension machine, and we can see it change significantly about the concept and also can further improve for the future as well. So I would like to acknowledge the support from all my funding agency on these projects. Thank you.
Thank you, Edmond. That was very insightful. That was a great presentation. Then I would like to welcome our next speaker, Zdenek Pliva from the University of Liberec. If you could please go ahead and share your screen. We look forward to listening and hearing into your presentation.
Oh, hello. Greetings from the north part of Czech Republic. My name is Zdenek Pliva. I'm with Technical University of Liberec since 1997, and my research interest is PCB design, manufacturing, testing, and so on, and some IC diagnostics. Liberec is on the very north part of Czech Republic, on the border between Germany, Poland, and Czech Republic. And our university was established more than 70 years ago, and our faculty, that means Faculty of Mechatronics, Informatics, and Interdisciplinary Studies, is one of the youngest faculty, and the next year we celebrate the 30th anniversary. Few words about our equipment. We have Dragonfly LDM2 and some other equipment for manufacturing and assembly, printed circuit boards, and some other equipment for three-dimensional inspection. That means industry CT machine. We are able to do cross-section analysis, spectral analysis, surface measurement, and so on. And we use, I think, standard tools or software, Eagle, Altium, Inventor, or Fusion 360, SolidWorks, Creo, MATLAB, ANSYS, TIBCO, and so on. I would like to present only two cases which were developed in our university. First is PCB bioreactor. It was motivated by our colleagues from Faculty of Textile Engineering, and they bring us the bioreactor, which is on the right bottom part of this slide, which is made from glass. It's expensive and they are not able to change design, so they asked us for another approach, and we offer them a Dragonfly machine to print such a equipment bioreactor. The aim of the work was that electrical stimulation of the cells is a really trendy approach nowadays, and it helps to culture or to enhance cells proliferation, orientation, and differentiation of the stem cells. And for this stimulation, it's essential to have a biocompatible and conductive scaffolds and, of course, the bioreactor. At this moment, we are able to produce conductive nanofiber scaffold, and we are aiming to develop new techniques with PCB technology. That means printed bioreactor. Just to describe how we use it, in this PCB bioreactor, we can place nanofibrous scaffold, both conductive or non-conductive character. And on the top of the scaffold, we seed the cells. Some specific cells type, but for the first experiment, we use mice fibroblast 3T3 type. This bioreactor is connected with some control equipment, and electric field is made between the tracks. For the first experiment, we use 100 micrometers thickness or width of the wires and isolation between wires. And then we monitor the cell behavior and the changes in the cell morphology, their orientation, and the differentiation of the cells on the top of the scaffold. We have to approve ourselves that the used inks, that means CI, conductive ink, and DI, dielectric ink, are cytocompatible with the used technology. We provide entity test, and you can also see UL certificate of non-dimension, which approve that this type of bioreactor is safe and appropriate for such a cell culture. Currently, we are developing methods of cultivation the cells in more detail. So new PCB architecture design, that means different thickness, track width, different orientation of the electrical field, and so on. Parallelly, we develop new electric stimulation parameters, or define these parameters and the control system of the electrical field. And of course, in vitro parameters, that means density of the cells, their type, and media composition. On this slide, you can see next printed bioreactors. That means new electrode shape, different stimulation, and we try to compare the results so that we design area of the bioreactors and we compare the results in every bioreactor to each other and to be able statistically evaluate the results of such an experiment. The second case is oriented to the printed inductive planar sensor of low frequency EMG fields. So the motivation of this sensor was the situation that pacemakers, which are used in the human body, are fully shielded, wires also, but the electrodes are not. And the simulation is similar with the electrostimulation of the brain. So the result of such a experiments or research can be used also on some cochlear implants and so on. External electromagnetic field has interfaces with the signal from the electrodes, and that means that there is some noise which is not known or measured. So for this reason, we need some source of external of measuring external field, and that's why we design a special printed coil. We assume the inductive sensor will be placed also on the patient's skin, similar to ECG or EEG electrodes, in the same shape, the same technology. This is the first result of our planar sensor. Number of the conductive layers is 10. On each layer, we have 8 turns of the coil. Thickness of the sensor is 2 millimeters. Outer diameter is 10 millimeters. Gap width is 250 micrometers, and the thickness of the conductor is 70 microns. And insulation layer is 200 micrometers. So the whole design or characteristics of this design is that we have a spiral coil in 10 layers. These coils are connected to serial connection. External dimension corresponds to the size of cell adhesive ECG electrodes, and it's a very good use of the space in 3D. So we are able to design a fully 3-dimensional design of such a sensor. We are not limited by standard PCB design or manufacturing technology. And the results very good matches with the ANSYS model. We provide some measurements. At the first beginning, we compared the results in range from 100 Hertz to 100 kilohertz. Serial induction is 27 microhenry, and resistivity is more than 23 ohms. Here you can see some cross section, so you can see that it is printed. It is not very orthogonal cross section, but I have to say that it is not in a real middle of the holes. And in the next generation of this design, we will use not wire design, but fluent change of the layer from one layer to another one. This design is very miniature. We design a planar sensor without ferromagnetics with very good use of this area. We are able to measure the field from microtesla to Tesla with wide frequency range, with quite good sensitivity for use in biophysics. Using this technology, we obtain high winding density in comparison to the conventional technologies of standard PCB, and 3D imaging of the external electromagnetic field to determine its effect on a living organism. At this moment, we ask our colleague in cardiac center in a regional hospital of Liberec to make some clinical research for using in their diagnostics or therapy. And we are working on a wearable application for long-term monitoring. And it's validated for non-invasive use in clinical research on the human body. Here you can see the laboratory equipment where we measure the behavior of these printed cells, verification of the sensor parameters in Helmholtz coils, in the field range up to 10 microtesla at frequencies 50, 100, and 150 hertz. And the results very nicely corresponds to the expectations. So at this moment, we are designing the next generation of the sensor. So we try to reduce the Wearable thickness and to enhance capacity miniature sensor for monitoring static electricity and some surface charge. And we use it in neurology research in cooperation with our colleagues from hospital. So at the end, I have to thank to Nanodimension for support us and everyone who helped us, because we had to prepare some special design and special manufacturing process. So we are looking forward for cooperation not only with our hospital but also, for example, with you. Many thanks for your attention, and Gerd, remind me one story which happens at the end of last year. If you mentioned the needles, here you can see what can happen if the DI had stopped the printing in the middle of the process. It is not intended, but you can see the printed needle. So if you need it, just switch off the DI dozen and you can obtain needles. So again, many thanks for your attention. Have a nice day.
Thank you, Zdenek. Okay, then we'd like to introduce our next presenter, Vincenzo Mastronardi from the CBN-IIT. If you could share your screen.
Yeah, okay.
Great. Thank you so much.
Can see it?
Yes.
Okay, perfect. So thank you, Natalie, for your kind introduction. And thank you for inviting me to this webinar on additive manufactured electronics for biomedical breakthrough. And today I would like to show you our last advancement in using additive manufacturing technology for healthcare applications, and especially in in packaging wearable devices used for monitoring of human biophysical parameter. So our purpose, the purpose of our research is to create, to develop a skin body system that is able to record and at the same time actuate and measure physiological signal by exploiting a number of sensors that can be located in different parts of our body. Sensor that can be, an example, piezoelectric smart patches that can be used for cardiovascular measurement activity, but also for monitoring muscle and sleep activity, but also by means of brain probes able to detect and measure disorders and also perform a control of the disorders themselves. And thanks to also the feedback coming from specialists and technicians and medicians, our system aims to also perform an actuation for the control or for a fine control of the therapy for that for those disorders. The final purpose is to develop a digital twin of human body that allows to have an accurate and robust model of the human body itself, acquiring real-time and real-time data, and do perform an analysis of this data exploiting artificial intelligence learning. For these reasons, we have developed a closed-loop healthcare that includes the fabrication and the development of different kinds of sensors, such as sensors for healthcare that are based mainly on a piezoelectric effect, on piezoelectric materials such as chitosan or aluminum nitride piezoelectric material deposited on flexible substrates that makes our device very, very flexible and conformable to curved surface. But also we are able to, we developed compact RF antennas made on silver ink on polyethylene and naphthalate substrate that can be used for communication of the acquired data, but also microelectromechanical systems such as piezoelectric micromachine, ultrasonic transducer that can be used for actuation purposes, and multifunctional neural interface with the deep brain regions. And I would like to focus this presentation, especially on these two applications, means the piezoelectric micromachine ultrasonic transducers and neural probes interfaces. In the last part of the fabrication development of our devices is made into the backend lab, where we have all the technologies that are useful to achieve the second part of the MEMS and the devices microfabrication. That means not only the mechanical and the electrical characterization, but especially the packaging of the single chip and the characterization and the testing of the packaging itself. And it is allowed especially thanks to our multi-material 3D printer coming from Nano Dimension. This is the outline of the remaining part of my presentation. So as I mentioned before, I would like to show you these two technologies for the human body, means tapered neural optical fiber interfaces and piezoelectric micromachined ultrasonic transducers, and how Dragonfly 4 enabled some solutions for the packaging of these devices before going to conclusions and acknowledgements. So the idea is to develop bidirectional optoacoustic systems that on one side includes in the same devices an optical emitter that allows the brain stimulation by exploding the light, and on the other side, on the same system, we are trying to integrate also a receiver that is an ultrasound receiver that is able to acquire the neuron's acoustic response as in the shape of ultrasound waves. For these reasons, we developed these tapered neural optical fiber interfaces with multiple functions that, on one side, is able to perform actuation purposes, such as the control of brain functions by optical, temperature, or drug delivery and on the other side, it is also able to sense the response of the brain cells, of the neurons, by performing a readout of the brain activity that can be either optical, electrical, or chemical. So our fiber optics probes has been equipped then with some optical windows that are located in different position of the tip of the fiber itself. That is a tapered tip, and these optical windows are used to provide the light for a selective stimulation of different regions of the medium in different regions of the brain. In example, the cerebral cortex or the hippocampal region. On the other side, since the probe is also able to perform sensing analysis, the probes, the optical fiber probes, have been equipped by metal electrodes that have been microstructured using 2-photon lithography that allows us to pattern very small electrodes on carved surfaces, such as the surface of the fiber, of the optical fiber. And these electrodes have been placed near to the optical window to perform an electrical monitoring of the light stimulated or the normal neural response of the brain. The main challenge in using this device is to perform an external contact of an highly non-planar devices that is actually the fiber, the optical fiber. It needs a backend solution to interface the electrical and the optical channel with the external acquisition system. And for this purpose, we tried to exploit the potentials of the Dragonfly 4 to build a custom PCB board that has this customized shape with a recess in the middle that allows to place the optical fiber and the small ferrule on one side, but it also includes the soldering pads and the connection pads. The soldering pads used for the external connections to standard readout electronics, and the connection pads that goes directly to the pads located on the tip, on the tapered tip of the fiber. The development of this PCB board required an engineered process to build and to embed the PCB board, the fiber into the PCB board, and for these reasons, we used we included in our design a stencil mask all around the PCB board that allows us to remove the first part, the first portion of the PCB from the printing stage, then place the fiber into the recess, into the housing region of the PCB, and glue the fiber itself by using epoxy resin. Then exploding the stencil mask all around that are still into the printing substrate, we can place again the PCB with a very small error inside the stencil in the printer to print the second part of the PCB board, that is the conductive pads printed on the top of the fiber, and the dielectric cover still printed on the top of the fiber, that allows not only to embed, to directly contact the fiber on the PCB, of the printed PCB, but also to completely isolate and strengthen the fiber once it is placed into the custom PCB. Following this kind of PCB, we have also developed different kind of PCBs, like the PCB for a single electrode optical fiber, as in the left side, in the picture on the left side, but also a more complicated PCB board that includes 4 electrodes, as the PCB showed in these pictures. So in this case, Dragonfly enabled the packaging of highly non-planar and curved devices, such as the optical fibers. The second application of the Dragonfly is the packaging, the self-aligned packaging of piezoelectric micro-machined ultrasonic transducers. We have developed this kind of devices for different purposes, not only to be embedded in, together with the optical fiber, as mentioned before, but also for ultrasonic medical imaging, for the blood flow measurements, in example, exploding pulse wave velocity, and for photoacoustic imaging. For these reasons, we have fabricated PMUT arrays, to the arrays that works at a central frequency of 6 megahertz. And again, we have tested these devices, but again, the main challenge is still reach the devices without using the standard wire bonding for connections of the pads all around the silicon die. Again, additive manufacturing technologies allowed by Dragonfly enabled us a solution that consists in printing of a PCB board that allows to directly embed in a self-aligned way the silicon chip, and to cover and enclose it, encapsulate it, including not only the isolation part, but also the connections that goes from the pads on the chip to the base connectors. Again, we have engineered our fabrication process for building this PCB, and the fabrication starts with the printing of the base with a customizable connector footprint that include also announcing where the silicon die is placed. with a thickness of this housing that depends obviously on the thickness of the silicon die itself. In our case, it was around 350 micrometer. Then,
Vincenzo?
yes.
2 more minutes. 2 more minutes, and then we have to make it a cut. Sorry, go ahead.
Okay, thank you. Then we interrupt the printing to place the silicon die into the housing for a direct self-alignment before printing the top enclosure frame and the metal tracks to the connection pads. At the end, we have tested especially the electrical continuity of our connection, and we found that the electrical continuity is still really fine. So Dragonfly allows us to skip standard wire bonding for the connections, achieving a PCB and a package that is very thin, less than 500 micrometer. So this is the last slide of my presentation, and I would like to thank all the people and all my collaborators, so all the team, and especially all of you for your attention.
Thank you so much. I'm sorry for interrupting. I'm just like, we're running out of time, and I just want to make sure that we also get to do the Q&A. No, it was a great presentation and really interesting with the mouse implant. That's new to me as well. Just to answer some questions beforehand, yes, the slides will be made available as PDF. Everyone who has registered will receive the recording as well as the presentations presented today by our key speakers. I think on the technological side, people are asking about the 3D printer itself, and that's something that we would like to take on. So we will send some additional information about the Dragonfly. So don't worry about that. We have some more specific questions. Gerd, I think this one is more directed to you. What bioabsorbable polymers were used in the cardiac implants? It's one of the first questions.
Say that again. What
absorbable polymers were used in the cardiac implants? And then it gives some examples of the materials: PLA, PGA, or PDLA.
Well, what we tested were the electrode and the electrode materials. So we did not really concentrate on the compatible materials. So what we really used as a carrier material was normal PCB material, so FR4.
Okay, great.
This is not for implants. So this is for testing out the electrochemical pickups.
Okay. I think in a similar fashion, someone asked what needle manufacturer we're utilizing. If you want to disclaim that here, if that's proper.
Not really at this point.
Yeah.
So,
okay, good.
Yeah. Mm-hmm.
No worries. Okay. Then we also had a general question. I think this goes to all of the current key speakers. Why are you not using FPC flex circuits in your designs? I think Edmond, would you like to answer that one first?
So why are we not using the flexible?
Yeah, flex circuits, exactly.
Yeah, so for the MEMS chips application, that one because the flexible material, we have a trouble to populating the chip on the flexible material. Maybe it's just our method that we try to bond our chip to the flexible material. We are not successful, and then but when we using the nano dimension circuit board, we have good successful. So yeah, but on the other two application, one is I printing the full bridge strain gauge directly on the on the chip with the multi-layer, on the circuit board with multi-layer, and the other one is a very tiny sensor that is not feasible to print in using the flexible material.
Yeah. And I think the same question, since Vincenzo had a great application. So in your regard, flex circuits, is that possible in 3D printing them for your application? Vincenzo?
I didn't understand your question, Natalie, sorry.
So no. So one of the questions, why don't you use FPC flex circuits? But in your presentation, you have a flex kind of design up in the application. So in your understanding, what are the advantages, or how well is that functioning for you with a 3D printed AME application?
Yeah, the main advantage is that in the first application, when I discuss about the optical fiber, it's really challenging to do the connections on the pads that are on curved surface, a non-planar surface, such as the optical fiber surface. So in that case, we have a big advantage from this kind of PCB printing, because we can additively add directly on the pads the connections, and move from the pads to external circuitry. And the same is on the second application about the PMUT, because when the number of the elements of the single elements that are present in our probes increases a lot, it means a lot of wires if we use the standard wire bonder. In that case, exploiting again additive manufacturing technology, we can print directly not only the connection pads in a single, let's say, in a single process, but also embed and completely isolate the device from the external environment. Especially if we in environment that are not dry, like wet environment, in example in brain, into the brain.
Hey, great. Thank you. That's an excellent answer. I think our last question for today, just because it's also late and we're running out of time, Zdenek Pliva, with regards to materials. So how important are the materials you use in creating your applications, or what is the testing requirements that you have to look out for?
I have to say that we can use only the two materials which are provided by Nanodimension. That means CI, conductive ink, and the dielectric ink, and there is no chance to replace it till now. In future, I think that we would like to use new isolation material which is more compatible to standard FR4 materials, especially for soldering purposes. And at this moment for us, it was the key topic was the biocompatibility of this material for the cells which we use in our experiments. So it was the first step to assure ourselves that the materials are not toxic, that it is possible to use it in medical research, and it was approved. So at this moment we focus on new design of the electrical field, a new measurement technology, or new technology to create a dynamical, changeable field inside the bioreactors. And speaking about the coils, At this moment, we would like to mount it inside the standard use in hospital, just to assure that we are able to measure outside electromagnetic field and subtract this noise from the measured signals from EEG or ECG equipment. So at this moment, just about the two materials, and we are not able to change it. Although we would like to use more than two ones, but at this moment it is not possible.
Okay, great.
And
Well-
can I add one more? Yeah, just
Go ahead.
one. Okay, sorry. So beside the flexible, like I think one of the advantage of the nano dimension machine is the custom shape. So I can 3D print the shape that I custom on my design. So that is something not available using the flexible material. So this is the major difference as well, because I can make it very small, tiny, and customized for the shape that I would like to. Yeah.
Yeah.
Thank you.
Yeah, I know. Yeah, that in general, that's the most fascinating part about using the Dragonfly 4 is customization and in-house prototyping. I think that's the biggest advantage that we can deliver at the moment, where people design and have to ship out or find a partner to develop and then print it or create the design. This enables you to just do everything in-house and work with one team rather than outsource. Okay, I think this pretty much sums up our webinar. Thank you so much for participating. Also to the attendees for joining us and asking great questions. Again, you will receive the recording. We will also have the presentation